try to apply to that. Supposedly it's like 35K a year. And I'm like, okay,
Wow, money.
that'd be great.
Hello.
Hello. I should say congratulations to you.
Yes, thank
Good
you.
job.
Thank you. I'm just grateful that it's over.
Yes.
I'm grateful that's
Not
beginning.
any more exam, of course, those classes you need there.
Right.
But yeah, that one you all you can focus on your
You
research.
you completed all your
All fired.
well done. Congratulations.
I was a little bit confused by the homework question.
Which one?
4.3.
Uh-huh.
I think I was just confused by the probability.
Uh-huh.
Maybe I went about it the wrong way.
The probability is the square and you just integral from the range, right? From given range.
Yeah,
Uh-huh.
from the range 0
If it asks you from 0 to some numbers,
to,
right?
yeah.
No, it didn't, it said around there, so you had to do from epsilon to epsilon.
A very good question. 4.3, right? Which one?
4.3.
No, but which number?
E.
E. Calculate the ratio of the probability of finding electron near the and 0. Near that one and 0. Okay.
This is the part that got me to why.
Yeah, that is just the function at that position. No integral. Integral is from which range of the probability. Okay, you do that way is more precise.
Yeah.
Yeah. Or just
Well, the thing that got me
yeah.
was that doing it from, when we do it from 0 minus epsilon to 0 plus epsilon, this part goes back to being psi 1, so it then becomes 0 minus epsilon,
Appreciate it.
0 of psi 1 squared, plus 0 to 0 plus epsilon, psi 2 squared dx. And I know that
No, that's why you make it complicated. Okay.
because it says around 0, and and psi 2 starts at 0, right?
Let me ask you. Psi 1 x equal to 0, b equal to psi 2 x equal to 0, right? That's the boundary condition. Is that correct?
Yes.
So your probability x equal to 0, you just do either, because both are same, so either take this one or psi 2, because they are same at this position.
Yeah,
And the
they're the
ratio.
same at this position. That's why this integral works, but not at minus epsilon plus epsilon, right?
Right, so if you do this one, yes, you do this one, yes.
What is
Minus
the-
this one, so that will make things complicated.
I just overcomplicated
Yeah,
it.
yeah,
Yeah,
kind of, but
yeah, I'm
if you do this one, I will give more credit.
Well, don't give too much credit because I basically wrote out the formula and said I'm not solving that, but I'm pretty sure it's 1.
So your question is just like x equal to 0, and whatever is x equal to some others, right? About 10, something, right?
-10.
Okay, whatever, just substitute this function when x is to that one. Because square is this probability, right? Since you are all normalized. It's hard. If you need time to do, that's fine. You can turn, for example, tomorrow, put into my mailbox. You know my mailbox over there, right?
The one in the.
Yeah, you can see because the number 2 from top, the most far right. Take it out. And it's specific. The one with the most, it's more complicated. It's up to you. Okay, that's actually. I think if you need tomorrow. Yeah, if you think you're done, then just give it to me here. If not, then you can still spend time and then put over there.
Would this,
Yes.
I feel like that would not be square integrable for the wave function in the potential step. Because psi 2, whenever you set it equal to 1, then the psi, these cancel out, but then you still have x from infinity to minus infinity.
That's why not ask you to from what, okay. You mean that is normalized? I need to find that. It's you psi 1, right?
Yeah.
But we didn't ask you to do this from minus to positive, right?
I'll tell you the results.
Just give you a range.
Right.
Yeah, just the range. So just if you say,
Near that 0 and
yeah,
here.
only
I'll tell you the
the
results.
E is asked the probability, right?
Right.
Yeah, so only that one,
Okay.
that particular numbers. That's yeah.
Oh, sure.
All right. So
I feel pretty good. The third and fourth one, I put true. But the first two, perfect.
before we keep continue, I want to I think he didn't hear, but I already taught him this morning. He raised the question about, remember I say when this go to 0, we go to the classical limit, and Tails asked, how can we understand this? I just very simply say that is compare with the physical quantity. Now I want to give a brief summary about this, and this topic actually is chapter 3 and section 8. We didn't discuss since the time. So if you you can also go back to see this section in particular, 3 and 3. So the question is, what is condition for classical limit, right? But we start from quantum. We know all systems we follow the quantum mechanics. But why the classical mechanics still work for most cases? That is, then we are going to see how we transform from quantum mechanics to classical. That means which conditions such that we don't need to consider quantum, we just consider classical. So that's this one, and then the answer is this one. It's a scale in h bar. So what that means, if okay. Okay. If the dimension of an action of system, so dimension is comparable with h bar. I mean, dimension h bar is joule per second, right? So you look that quantity and then compare with this one. I mean, this is not compared. If the dimension is let's say this one, then we're going to see if such value is comparable with h. That means the value is, I mean the value, the size of this value is comparable with h bar. That means you cannot ignore the h bar. Then I have to go to quantum mechanics. That means we cannot ignore this effect from quantum mechanics. But if this value is much, much larger than h bar, or in a sense we say h bar go to 0. So does not mean h bar value go to 0. That means that quantity compared with h bar, this is very, very small, so this one very big. Then the classical limit, or we can use classical description, which is enough to describe the system. Okay, or alternately, we use lambda. So that is a scale in terms of h bar, this scale in terms of wavelength, which is a de Broglie wave, right? So de Broglie wave, we know that is h or p, right? So in this case, if the lambda is comparable with the size of systems, then we go to quantum mechanics. We cannot ignore, in particular, the wave-particle duality. But if lambda is very, very small, go to 0, that means, or let's say this way, much, much smaller than the size of system, then we go to classical mechanics.
Does this imply that expectation values of observables should not have an h-bar term?
should not have what, H bar.
Yeah,
Okay.
because the expectation values of observables in quantum mechanics.
Yes, yes. That is, okay, now I'm going to give some examples. So let me answer the examples. In first one is your case, right? So in quantum mechanics, we know the expectation value, the time evolution expectation value is scaled by this one, right? You mean, and this commutator between this operator and Hamiltonian. And of course, there's a time partial derivative. So if this is 0, then go to only scale by this one. Okay, that is quantum mechanics. And classical mechanics is quantitative. Some of you already take, you have not yet, but you already take my classical theoretical mechanics. Remember this chapter 9? Okay, instead of to distinguish the commutator, I'm going to use this one. And if in this case, if this go to 0, it's go to just, do you remember that this is a Poisson bracket? So what happened is, if this quantity, because this compared with this one, is comparable, we cannot ignore this term because this one is some order of the H bar or 0.0 H bar, something. So we have to go to the quantum mechanics. But if this term is much, much larger compared with this one, so we can go to the classical. Then we go use this formula. Instead of this quantum mechanics, we consider that each quantity has a corresponding operator. So that is a commutator of operator. But in the classical, this is a point bracket. And this Hamiltonian operator, this Hamiltonian. That is my case. Now let's give another case, and I hope that can help you more. Case 2. Chapter 1, we discussed at the beginning of this quantum, we just discussed some of a failure in classical mechanics. One of is black body radiation, right? And in that case, if you remember, the quantum mechanics, it is the average energy is this formula. If the quantize introduce H, remember the Planck introduced this, so energy is quantized. Then to calculate the average, we use this partition function in the statistic. So we have, positive, yes. That is quantum mechanics. But classical, in that time, we do not have this. So classical mechanics, with this statistic, consider energy spectrum is continuous. That is just or partition, energy equal partition, the energy theory, right? So how from here to here, in which condition? So if H mu is much, much smaller than KT, that means this value is much, much larger than this one, then this one. So we can do this approximately equal to, we do the Taylor expansion and just up to the first order, right? 1 plus T minus 1. So this one canceled and that is. Okay, so that is condition. If this happens, then we can use the classical limit to represent the average energy instead of use quantum mechanics. So that is, if you say that means, okay, this term, or you mathematically just look, this term is close to 0, you can use Taylor expansion, right, mathematically. So basically, this term much larger than this one. Now, number 3, tunneling effect. That is the question come from, right? When we discuss tunneling effect, so just remind us again. So we have transition coefficient, which is 1 over 1 plus 1 over 4 epsilon, 1 minus epsilon. Hyperbolic sign square, I think, lambda, square root 1 minus epsilon, right? So remember lambda is A over 2mv naught h bar. Epsilon is E over v naught. That is quantum mechanics. And we already said that is non-zero, so we have a tunneling, even we have an energy barrier. But if this term is much, much larger than this, so what happened? That means lambda go to infinite, right? Well, very big. If this ratio is very small, so this is much larger, this ratio is very, very large. So that means for very large, then the t approximately, you see this one go to infinite, so denominator go to infinite is go to 0, right? That is classical. Classically, we know there's no any transition with energy barrier such that energy is lower than energy barrier, only totally reflect. Okay, let's see the last one. Okay, not last one. This one is also interesting. Sorry. Heisenberg uncertainty principle. Heisenberg. Is this quantum mechanics? The fluctuation of x or uncertainty of x multiplied p always larger or equal to this. This is a quantum mechanics. What does mean? The fluctuation scale is comparable with this h bar. That means we cannot ignore this fluctuation. But if whatever the delta x or let's just say product, this is a fluctuation, right? Distribution is okay. This fluctuation is much smaller than the measurement accuracy. So we do the measurement, and that's definitely depends on system, right? So suppose if we measure this bullet, the size is much larger than this in this case. So that's the classical limit. So in that case, this difference is almost compared with accuracy. For example, our accuracy, if the accuracy in terms of the 10 to the minus 3 meter. Then this one fluctuation, if I compare with this one, is about 10 to the 30 minus 30 something. Let's just say
34?
yeah, 30 something, right? Just the 30, for example. Okay, this is a meter, right? This is a product, and so that the product, this one, and I'm not sure this product is how much. Suppose is with if we say I can go more accuracy up to 10 to the minus, even minus 10. I'm not sure we can reach that accuracy for the classical system. Then you see this one is so small, so the fluctuation compared with accuracy is almost 0, right? That means in that case, we will almost say this can be 0 and this can be 0. That is classical. So that depends, your measurement, you can measure the accuracy and the fluctuation, which compare with how much you can measure. Since this fluctuation of quantum mechanics is this over, with this level, right? So you just compare this case. If that happens, then we go to classical mechanics. That means this fluctuation does not play or can be ignored. Last one. Last one, let's consider this de Broglie wavelength, right? And we know that is for the probabilities. Lambda is this value. Okay. So in quantum mechanics, the lambda should be comparable with the size, right? Size of system. Then we have quantum mechanics. So example, homework 1, we calculate the product, right? The product. It is about 10 to the 15. Remember this? And what is the size of the nuclear?
A bar.
Minus it's about this picosecond, so that's at least that's 12. At least, right? Less in the angstrom because in the nuclear, right? So you see they are comparable. Then we have to take into account this wave behavior. But in classical mechanics, so the lambda is much, much smaller than the size of system. Example is, we also calculate bullet, right? Remember this? We have something about this table. And what the size of bullet? Size, if I use L, B, at least in this one, right? It's almost very small already. So you see how big the difference. So in this case, this one almost 0. So we can say, okay, in summary, when you just, what you want to see, just you use the either H bar or lambda. You can consider both as your scalar parameter. See, so if this go to 0, it does not mean this exact go to 0, but just compare with what we compare the system. The quantity of the system or the size system go to 0, then the quantum mechanics go to classical mechanics. That means use classical mechanics is enough to describe the phenomenon of system. That makes sense? Okay. So I think if you can also go to the chapter 3 to read that section. On the second question, I think I didn't answer clearly, so now I want to answer it again. This for infinite well, right? And Tyler asked question, say for n go to infinite, this is an indistinguishable, right? This question. So now let's see here. N, I'm going to use, instead of to see this delta n divided with n when n go to infinite, that may not be easily to imagine what the difference, but let's see this one. Just see this 2. If this 2 has difference, then we can distinguish. If not, we cannot distinguish, right? So this one is n plus 1 square and n square, right? Then when n plus 1 square, when n goes to infinite, is almost n square, and is 1, right? So that means if n go to infinite, you cannot distinguish this one and this one, so they are equivalent, or you cannot distinguish. That makes sense? Right? Okay. And that is also like, see, if we have 2 high mountains. One is slightly higher than others, that's the difference. But this mountain's height is proportional to the n squared, right? So that means increase with this level. And you can see the difference is n. So that difference compared with the total, you cannot distinguish. Yes?
I'm tracking with everything, but what is the, so when we look at the ratio, we come to the conclusion that they're indistinguishable at n goes to infinity. But I feel like it's a little bit unfair, because what if we did the limit as n approaches to infinity, you have an e of en plus 1 minus en.
Yeah, that's
instead of the ratio. That would be infinity, which we would then say we could clearly tell the difference.
That is, but you see this one. This one is, if you do this one and go to infinity, this is the n squared, right? This is the n, 2n plus 1. So that means kind of a ratio is infinite and infinite squared. So this one, because go to infinite, so this one much larger than this one, and that's why we go to 0. So compare with infinite square, It's infinite, even though each individual is infinite. But if this one is increased very, very fast, the infinite times of another infinite, so you see, that is different. Maybe some numbers, if you look this, just give you one, for example. This is not energy, just consider if we have the one is this one and this one, then go to 100, so the difference is only one, right? Just 2 order less than that one, so you may sometimes ignore the difference. That is what we need. Okay, good. Now let's continue our example. We discussed this, the infinite square wheel, and we do some practice. So we finish some of them. We just have the last one. So now, just rewrite the energy and the function, right? And I think square root 2 over a sine a over m pi x, right? And from 1 to infinity. For this case, we do this, we have to calculate this one, we have to calculate this one, and this, right? We will finish. And from here, we can estimate that is, we do this, we only finish it, right? So just go see that we discuss rest. I will pass that. Now, another issue which is interesting is here. This is a potential wheel, infinite potential wheel from 0 to 8. Okay, that is this result. And we have discussed this, we can also discuss P1 is approximately equal to pi h bar a, and from this estimate we also obtain this ground state energy is pi square, h bar square pi square 2. Right? That is we also discussed. 1, 2, 3, 4, now 5. 5 is if we suddenly increase the size of the wheel from A to 4A. Okay, so now let's start the new one. It's A prime equal to 4A. So the particle has ranges from 0 to 4A, right? So that is different. Then ask the question, suppose initial is just the ground states. Then what is the probability of, let's just get probability of, before that, let's say let's first solve this one, right? Solve this system, we can do the same thing, so I'm going to use prime for this case. That is follow the same thing, right? H bar square, pi square, n square, 2m a prime square, right? The difference is only this the width of this wheel increase, but the formula with the procedure everything the same, right? So I just use the same formula, but now I replace by a prime, and a prime is 4 times a, so that is 16, and this one is 32, right? Okay, that is E prime. That is in the new wheel, the energy level. Then the wave function, I'm also use set prime, and n the same, right? N always from 1 to 3, right? This one, square root a 2 over a prime here, right? Same thing here, but just replace a by a prime. Sine n pi x over a prime. And then I can also do further, but you can keep a prime, but if you want to replace a prime by a, so now here is a 4a, right? Sine n pi x over 4a. And same thing, n still from 1 to infinity. Okay, now the question is asked, if the initial state is just the ground state of the previous system, then I just narrow here, and now suddenly you move this, so it became the new states, right? The new eigenstates is this one. So now what is the probability? First is in general we have also used. So that is the probability because this is initial and this is not eigenstates of the new one. So it became a kind of a general states. And these general states can be expressed in terms of linear combination of the new eigenstates, right, in general. But whatever, that is states, now we are going to see what is the probability of the particle initialized here, then after sudden changes as well, the probability from this system at the ground state of a new well. So that is 1 prime, upside 1 prime. That is ground state. So this is a question, and this is a formula to correct this question. And the probability is the states project to the eigenstates of that system, right? And divided by the normalization here. If we write down here, I'm going to say prime, and this is 0 because here, right? This is the initial, the narrow well. That ground state is this one, so I have the formula. And we know this is already normalized, right? So we have the normalized factor here. So that is equal to then now you can do the formula here from 0. Okay, here is something I want to go to even detail. So here in principle, the probability from minus infinite to infinite, right? Okay, now this one is the 1 prime complex conjugate. That is this. Then we go to next. Here, psi 1 prime is from 0 to 4a. But this product, psi 1, only non-zero from 0 to a, right? Otherwise 0. So this interval is to here, right? Not to 4a. That makes sense? Because other cases are all 0, this function. So now you are going to do the integral is this. Makes sense? Then the remaining part you just go to. So this one is square root here. This one, right? 2 over 4a, so that is 1 over 2a. Another is 2 over a, right? Okay, let me just one by one. So this one, and then a equal to what, right? Sine pi x over 4a. That is psi 1 star. Psi 1 prime star, right? And then the psi 1 is square root 2 over a. Is this one? When a equal to 1. Sine pi x over a dx. From 0 to 8, not from 0 to 4a, because this one only non-zero between 0 and 8, right? Then the constant you can, the remaining part I will not do. This is very simple, right? Math. Let me give you, I think this is also one of the problem in textbook. Let me give you just the final result. Here is sine alpha multiplied sine beta is half of the cosine alpha minus beta minus cosine alpha plus beta, right? Just use that one. Okay, let me write that. Next step, so that is 1 over a, right? Square root, and then from 0 to a, so I'm going to half of cosine alpha minus beta, so that is pi x over 4a minus pi x over 2a minus cosine pi x over 4a plus pi x over 2a. Sorry, 8, not 2a. This is 8, right? X. Then the remaining you can do, right? So now I give you the final result is, okay, I forgot to take a square. So that is, then finally we have a square over, we have a factor 2. Okay, inside factor 2, so now the inside is half of 4a over 3. Yeah, 3 pi sine 3 pi x over 4a 0 to a minus 4a over 5 pi sine 5 pi x over 4a from 0 to a. And this gives us numbers is about 0.658. So most probability, but it is not 100%, right? So this one. Second one, you can also do another. The probability to find the second and the first excited state. So okay, here usually they may ask like this, even prime. So that means the system which found the system in the even prime. Initially it's even, right? And go to even prime, what is probability over E2 prime. So second one is if find the particle in E2 prime, you'll do the same thing, that is sine 2 prime x sine n x squared, which is sine 2 prime x sine 1 x. Well, I just give you the final result is 16 over 9 pi, which is 0.18. Okay. So this is I tried to answer the test question last time. You asked if from here to here can we make the system energy conserved or not? And you can see it is not conserved, right? Because from this energy level, when we sublet to here, it became the probability to even prime, E2 prime, E3 prime. The reason is when we make the sublet strip by external force. So something changed the system, right? So that is why the system that cannot keep the energy conserved. Okay, this example and the later homework, something like this, I think you can do yourself. Now we go to another example, which is similar to this, but just a symmetry. So we will use the same idea. We solve the result, the time differential equation, but the formula is slightly different. This is symmetric. Remember, this is unsymmetric since this potential is from 0 to a. Now we consider this symmetric. If the potential has symmetric potential, well, it's like this. Here, this is 0, right? So this is x. Now we have the symmetry here. So Ax is infinite, then x less than the negative half a, and 0 for in this range. And again, infinite when x larger than the half a. So compare with this one, just unsymmetric, this case, and this symmetric, right? Everything the same, because potential within the range still 0. And out of the range, out of this, the wheel potential function to be precise be equal to 0, right? Everything the same. So now let's just give you before this solution, we need to discuss the state parity. Parity. Since now we have the symmetry, so the parity issue is applied in this case. Parity, because we know this potential has symmetry, right? Whatever the next x and the positive x, they are equal, symmetric. So the Hamiltonian, if you use operator, is also symmetric, right? So what it means, if I use the parity operator and the Hamiltonian, are they commute each other? The answer is yes, right? And that is I think when we discuss this one, the joint eigenstates, we have first, this be commute each other. Second, the eigenvalue of H, right, En, is this eigenvalue H is non-degenerate, right? For given energy, we have a given function. So it is non-degenerate. So if we satisfy these two conditions, we can build up this joint eigenstates, right? Joint eigenstate I'm going to use is a joint eigenstates for both of Hamiltonian and the parity operator, right? So that is the analysis. Then we can have this solution for the joint eigenstates that also satisfy the parity or symmetry. Because this, so if I say that the function that's because this, so then this nx must have a real defined parity. The reason because it's to be also the eigenstates of this, the parity operator. That means we have either the symmetric, I use Sn, in this case, they're equal, right? So that is a symmetric, either we say symmetric or even function. That means this follow that, okay, that follow this one. That is eigenstates of pure parity, right? Okay, that is for this case, and for another group is this is a well-defined parity of symmetrical even. Another is minus x equal to minus antisymmetric. Antisymmetric or odd. Because that corresponds to this is also eigenstates of parity. With eigenvalue minus 1. Remember the eigenvalue of parity has two values, plus 1 and minus 1. Correspond to plus 1, that eigenstates be symmetric. This one. And for the eigenvalue equal to negative, that this eigenstates be antisymmetric. So that means when we solve the Schrödinger equation in this case, we say there's no parity, but now in this case we are going to solve the Schrödinger equation. So okay, the solution of time independent equation psi x in general mathematically it's the linear combination of this, right? Where k is but according to, right? But according to the parity, since the potential is here, so we have select, this one is antisymmetric, right? This one's symmetric. So we have these two, very easily we can find. For symmetric eigenstates, it's B, I use B cosine kx, and for antisymmetric, we have the form of A sine kx. Not a linear combination of two. This one has no parity. But since in this case we already analyzed if the potential has symmetry, then this eigenstates is joint accident with Hamiltonian and the parity operator. So the eigenstates should be have a well-defined parity, either symmetric or antisymmetric. We cannot take this one. That is, we first solve the equation, then we have a mathematical solution, but then we are going to use the physics to select physical acceptable wave function. So this is different from the previous one, which is not symmetric in the potential, so we do not have a parity on the wave function. Okay. Then once here, so how about now next step we are going to determine the allowed k value, right? And also this coefficient or the normalized factor. How to do that? Boundary condition, right? Yes, we always boundary condition to give us the solution for the allowed energy or k value and also the coefficient. Now we are going to use the boundary condition. How many boundary conditions? We have two boundary. We have also derivative, so totally 4 equations, right? Let me see. I think, all right. So that means for the symmetric, then x equal to negative half a is be equal to is symmetric when x equal to half a, right? So in this case, symmetric, when x equal to half a, that is cosine. Okay, so that gave us b, that equal to 0, sorry. Because at boundary is b equal to 0, right? Here, it's infinite. Oh, wait a minute, I made a mistake. Okay, yeah, that's correct. Two boundary, any case, this case be 0, this case be 0. I just combine these two equations together. This be 0, right? And this also be 0. So I just take the two boundary conditions together. So this immediately gave us b cosine kx, k half a equal to 0, because cosine minus alpha equal to cosine alpha, right? So the same thing. So from here, in this case, I just keep continuing here, then k half a is equal to half m pi n takes r number, right? Because we know when the cosine half pi, 3 half pi, 5 half pi, 7 half pi, all the even numbers are 0. So from here, we immediately got the k is function n, and 2 to cancel, so we have n pi over 8. N equal to 1, 3, 5, 7, R number. That is the first case. Second case, the boundary condition also for the antisymmetric. So we have antisymmetric. This negative half a is equal to 0. Then the positive half a also 0. So that's equal to 0. And from here we have a sine k half a. Okay. equal to 0, and another is minus A sine K half A equal to 0, right? So this both, since sine has negative alpha is negative sine alpha, right? When sine, I take the minus half A that equal to negative sine half A. So whatever plus minus is give us K A or half equal to 0. Sorry, equal to pi. This equal to n pi, right? N, if I use the same formula, but n are even number. That then the Kn in this case again the same thing, n pi over a, but n equal to 2, 4, 6. Since sine pi, if n pi, if n is an integer number, then half n should be even number, right? So we have both formula for Kn, same formula, but now one is for the integer number, odd number, another for the even number. Now we can combine. First, give the computation for n, energy. Energy is 2m, right? From somewhere, okay, here, right? Okay. So then we substitute whatever the n equal to the even number, odd number, the same formula. Then that is h bar square, pi square, n square over 2m a square. Now n can start from 1, 2, 3, all numbers. I just combine these two together. Since energy only depends on Kn. Kn, if a equal to odd number or even number, all the same, right? Formula. So energy, then what you can keep in mind that the energy is alternated correspond to either symmetric or antisymmetric states. Right? But n equal to odd number, that be symmetric, or even number, that be antisymmetric. Okay. So let's do that here. Then let's summarize this together. Is A cosine, now here K, cosine corresponds to this one, right? That is, I use the same here, so that is n pi x over A. But this n should be equal to odd number. And then that is symmetric, antisymmetric, sine n pi x over A, the n is even number. That of course this is important. This only within the wheel, right? Here, for this coefficient very easily, just normalize. Second. Then we can have, that's very simple, so I just give you the result is A is square root 2 over A, and B also the square root of 2 over A. Same. Okay. So we got the wave function, and then this wave function looks like this potential wheel from 0, half A minus half A. When the A equal to 1 is lowest, right? Correspond to E1 is lowest. So when A equal to 1 is odd number, which function is this one, right? It's cosine symmetric. So that is, sorry, which is symmetric. Then when A equal to, first steady state, A equal to is even, so that be this function. Then that is then go to 5. So you can see this symmetric is alternated. Symmetric, antisymmetric, symmetric, antisymmetric with increased energy level. This is the property of the potential wheel, which is symmetric. since they are similar with this result, almost the same with the unsymmetric. The only difference we have symmetric, so we have to consider the wave function to be forced to satisfy these conditions. Others are same, right? So here, you can see I skip the intermediate step to where we obtain this and that similar stated for this asymmetric potential wave. Now we consider this potential wave is infinite, so we can say the wave function of two boundaries be zero, outside the wave be zero. Now we consider the finite. How about the finite case? Finite square wave potential. So picture like this, let's just also take the symmetric as example, 0. Okay. This is V naught, this is V naught. Not go to infinite. And if not go to infinite, quantum mechanically, that means the wave function of a particle, the probability find the particle inside the potential wave, inside this area is non-zero, right? So let's see, it should be given this result. So now let's discuss this case. For energy, this energy, there are two possible. Here is energy larger than this one. We already discussed, right? When we discussed this, the particle with, I think one is the energy barrier, another is with the potential wave with finite. Remember we discussed this case. And energy. Then we know the particle goes here and the sum of perturbed by this one. But there's a continuous spectrum and this the transition probability we discussed already. So I will, this one already finished. I will not discuss this. Let's just go to the case if the energy is lower than the potential, this potential wave, right? So let's consider this case. This case, you will see this bounding. Classically, you will see that particles be always bounded between the half A, minus half A and half A. But quantum mechanics will show that it also have a probability to find particle outside this wheel. That is the discussion we are going to go in the next topic. Okay, so here, positive part, let's go. All right, let's consider the case. This case. Okay, for this case, then we are again we separate region 1, region 2, and region 3, right? So the in region 1, the Schrödinger equation or the Hamilton, the eigenvalue problem is minus. Let me just first give you the result, and I will explain why. Here. This one, if in this range is energy, let me give you K1. K1 is square root 2m V naught minus E, because V naught higher than E, right? So in this area, since energy is lower than this, when you solve the Schrödinger equation, you have the term when you move this E. Just give a general formula. General formula. Dx squared psi x plus 3 this jump too much. Let's keep on this way. Minus 2m h bar square A naught equal to minus 2m h bar square. Yeah, remember this? Because I just divided the minus h bar square over 2m both. So here plus became a minus here. Then you, this also minus, then you move to the right-hand side. Energy is positive, this negative. But because this one is larger than energy, so I take negative sign outside. Then the K here, this is positive. That makes sense? So that is the formula for region 1. And since it's negative, I just keep the formula, then we are going to discuss the solution. For region 2, since this one is 0, then when this is 0, when you put here, it's positive, right? So region 2 is plus K2 square sine 2x equal to 0. How about region 3? Same with region 1, right? So the formula or the equation minus here. Again, it's K1, right? In this one, there is a difference on this. So, let me give a K2. K2 is, since in the potential wheel, potential is 0, right? So K1 square sine 3. That is 3 equations in 3 different regions. Then each one we know the solution, right? Okay. Let me first give a general solution. Then we are going to use quantum mechanics and symmetry to analyze which one we are going to select. So we have psi 1 x. For this one, we have 2 a exponential k1x plus b exponential minus k1x. Here, no I. This is a real, right? Because it's negative. And 2x is a sinusoidal function, right? So that is c e by k2x plus b minus by k2x. And psi 3 again is decay. So I'm going to use e exponential k1x plus f e minus k1x. Okay. Now we need physically, right? So now we are going to discuss physically acceptable solution of functions. Which information we have to consider? First is be finite. So now let's look at psi 1. This one is x always negative. So x negative, this is when x go to a negative infinite, this one okay. But this one go to lose out, right? So we have to drop this one. Similarly for this one, x go to positive infinite, this one not acceptable, only this one. That is one thing. Okay. That is one case. Now, so first case is the function psi nx being finite. Second one, psi nx must be, see the symmetry of this potential. We have a symmetry here, right? Potential minus x equal to potential x. So we have a parity. Then the wave function speed has also parity, like we discussed just before. So here, I will define parity. So what that means, now let's come back to here. So now wave function, I'm going to say for the first one is considered, okay, any symmetry. Since here I have not given, let's just I have not discussed the quantized, I just consider wave, right? So then for the antisymmetric, that's B. For psi 1 here, we have the select A exponential K1x, right? Because we have a job this one. For x negative. And intermediate here, if antisymmetric with sign, right? Let me use C coefficient as a sine K2x. So, in this range. And here, we can immediately give the coefficient to make sure that it is speed antisymmetric, but let me first give here, and then we are going to find the coefficients to be satisfactory. Now here, dE minus K1x, right? For this case, you have job this one. No, okay. Sorry, the coefficient, okay, if we use coefficient here, now instead of D, it's SBF. Okay. And then for the symmetric, first one, again, we have to use A, right? Because only A. Let's see, I use the same option. Yeah, okay. Fine. And B cosine K2x. And I use E, right? Still F, right? But so far it's still not satisfied with symmetric and asymmetric. Only this area. These two have not yet. So we are going to determine this coefficient relation between these two to satisfy antisymmetric, and these two to satisfy symmetric. So you just keep in mind here. So now this be minus, here is minus K1 x. Okay. That is the formula like this, but we need to determine the coefficient such that we will have a real symmetric. How to do that? Boundary condition. We have a boundary conditions. Let's first consider this antisymmetric, then we consider this one by one. So first consider for antisymmetric. Okay, we have at x equal to minus half a. Okay, so let's consider this one. At x equal to half a is this one, and should equal to this one, right? So that means we will have a here. A and x half a is exponent minus k1 and half a, right? That is equal to this case c sine K2, right? K2 here minus. So let's go just minus half a. This is equation 1 I'm going to give. And then we are going to consider this half a, we also consider the first order derivative. So when we do derivative, we have K1 here. And the A1, K1, A exponential minus K1 half is also equal to, I use C, right? It's a C and then the K2. Then the cosine minus K2, that is equation 2. Then at x equal to half a, we also have two equations, these two. So first one is a C sine K2 half a is equal to F exponential minus k1 half a. Equation 3 is this one. And then the derivative. Derivative we have a k2 c sine, this is c, not parentheses, right? C here. Sine k2 a over 2. And here we have minus k1 at exponential k1 at equation 4. Okay, so now we have several cases we can do. Let's first 2 divided by 1. 2 divided by 1, you can see A cancel, CC cancel, right? So we have a K1 relation between K1 and K2. That we are going to use this to find the energy, allowed energy. So now let's get it first. K1 equal to negative K2 cotangent K2 A over 2, right? You see here, this one to this one, right? 2 in the numerator and 1 is denominator, so this cosine z, so that is cotangent. Now I'm going to give this one is as a 5. And then we can also, then the 3, 1. 1, 3. Okay. 1 and 3, so we have A and C. So CC cancel, right? So 1, 2, 3. 1, 2, 3 here, that is this divided by this, and this one divided by this. So CC, both sides we have 1. You can move this to this. Both sides of CC cancel, right? So this cancels only F very easily. F A equal to negative F. That makes sense? You just change. You can make this switch the positions in 3 and then you cancel, right? Okay, so this makes sense. Now with this one, and then we are going to, okay, so that one, then we go to, so from 1 we can, also find C is, we have a minus, this one, right? Sine minus alpha is minus. C is minus A exponential, K1 A over 2 and divided by sine K2 A over 2. So finally, now we can have this antisymmetric. Antisymmetric is A, and then you are going to determine A as a normalized, but that is not seriously. We have already the coefficient make this as C here, right? C is negative A exponential minus K1 A over 2 and divided under the sine K2 A over 2 and this this is X sine K2 A over 2. That is the middle term, and then the F is negative A, right? Okay, so then you can double check. In this case, it satisfies antisymmetric. When you have this X become a negative X, this is negative, this plus, right? And this one itself, because sine X is also change the sign. So yes, you can double check. If we write down this way, we can find it satisfy the symmetry, the antisymmetry. So, you can check yourself. So I just that is final. Now the coefficient only 8, so we can use the normalization to determine the 8. Similarly, here I can do this. Similarly, for the symmetric, we have do the same thing. x equal to minus half a. We have two equation. This is a exponential minus k1 half a equal to b cosine k2 half a, since cosine minus half and plus half same, right? So we can then same with one prime. And another is k1 a exponential minus k1 a over 2 equal to k2 b sine k2 a over 2. That is because cosine derivative is a negative sign, so negative, you have a negative here, negative can plus, right? That is for, and then at x equal to half a, we also have another 2, is a b cosine k2 a over half equal to, what I use, f, right? F exponential minus k1 a half, k3 prime. Then this derivative k2b sine k2 a over half equal to minus k1 f exponential minus k1 half a for prime. And do the same thing. So like 1 divided 3 prime, we have a equal to f, and 2 prime divided by 1 prime, we have this, this is the important one, k1 equal to k2 tangent k2 a half. This one I'm going to, since we are going to use this one, I'm going to see trigraph. So with this, and similarly, you can also have the coefficient from 1, you have the b is a exponential minus a k1 half divided by cosine k2 half a. All are same, so just this function itself is symmetric. Now finally we have this solution for symmetric. X is a exponential k1x, and b is a exponential minus k1 half a, and cosine k2 x cosine k2 a over half, and then there's a minus k1x. So you can check it is symmetric. Minus x equal to, I just leave it to you. Okay, so now we have the wave function, the solution. The next job is try to find a lot of energy, right? I know that is time, but let me first give the formula, then we are going to discuss next Monday. So this is the next job. We are going to find the solution for eigenvalue. Eigenfunction we obtain. How to do that? These two equations. Because this gave us the K1, K2 contain the energy, right? So we are going to use this formula to determine. So in order to do that, let's introduce some of our coefficients. Define alpha is K2 over A. And then because K2 is this one, right? So immediately we substitute alpha equal to 2me over h bar over 2k. So then energy is function of, let's directly use cancel the formula, 2h bar squared alpha squared over ma squared, which is a function of alpha. That means if we determine alpha, we get E. But this is a formula we have not find alpha, right? So this is the next job we are going to find alpha. Then we also, this is a defined first one. Second one, we introduce R, which is A over h bar equal to 2mv naught R. Okay. Just this. So that R is function of V naught. That means for given V naught, given potential will the height, we know that parameter. With that parameter, then we have V naught is function of, actually we don't need this one since V naught is constant. So then from here, then we have the K1, which is K1, if you remember that is 2m V naught minus E over H bar, right? And then we are going to substitute alpha, E is here, right? And the V naught, okay, and then we V naught here, V naught, so I'm going to substitute here. From here, V naught is 2H bar squared R squared over M A squared, right? Then we substitute this one here, substitute here, and then you can see K2 is very simple. Okay. So now we have this formula, then we are going to find this. These two are transcendental function. We are going to substitute the K1, K2 in terms of alpha and R. Then we are going to use the graphically, we can solve the, or at least qualitatively, not quantitatively, give the solution. We are going to discuss this in details on Monday. So this one is another example when we deal with the different type of potential, right? So you see the different type potential, the solution or the motion of the particle is totally different. And we need to be careful, and also that is system, specific system dependent. So that is we do the practice, and we have some of idea about this, how important potential is. All right, okay, and homework for the time is yours. If you finish, you can tell me. If you want to work a little bit, you can send to my mailbox tomorrow. Thank you. You want to do it? Okay, good. But if you have any questions, just let me know. Okay. Thank you.
I'm gonna keep thinking about that
That-
question 4.3.
Yeah.
So I might ask you a question, but I'm
Yes,
gonna turn it
you're
into
welcome. Come to my office.
Probability.
Yeah. I wanted to see if I could better understand that.
Yeah.
Can I erase here? Or, okay. You think you can do all you want to, which one is hard for you? You just pick hard. Okay, that's fine.
Oh, maybe it's not.
Okay, the last one? Okay, probability.
Yeah. I just got started on it. And
4.3, okay,
yeah, so
okay.
I'll probably have the same.
All right. Okay.
But thank you.
I'm gonna see if I can fix it.
Okay, all right.